Unit 6, Topic 4, Counting Principles. We're going to talk about how to understand and explain the fundamental counting principle, counting with permutations, and counting with combinations. The fundamental counting principle, given an experiment with events A and B, where event A has n possible outcomes and event B has m possible outcomes, the total number of different outcomes for the experiment is n times n. This extends to any number of events and their outcomes. For example, adding a third event C to the experiment with O possible outcomes, which I know is a little confusing with 0, but it's O possible outcomes, brings the total number of possible outcomes for the experiment to n times m times O. So here's an example. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read during the quarter? In this example, let me make this a little smaller. So in example 1, you would have 21 times 18, and when we do that on the calculator, we get 378. So that means there's 378 combinations when you have 18 or 21 novels and 18 volumes of poetry. Example 2 says, suppose at a particular restaurant you have 3 choices for an appetizer, soup, salad, or breadsticks, 5 choices for a main course, hamburger sandwich, quiche, fajita, or pasta, and 2 choices for dessert, pie or ice cream. If you are allowed to choose exactly one item from each category for your meal, how many different meal items do you have? So in this example, now we have 3, right? We have 3 options. We have an appetizer, we have a main course, or we have a dessert. So there were 3 choices for the appetizer. There are 5 choices for the main course, and there are 2 choices for the dessert. So in this, we have 3 times 5 is 15, times 2 is 30. So that means you have 30 possible selections. All right, so here we have a little supplemental review of factorials. The factorial of a non-negative integer, n, represented by n with an exclamation point, is the product of positive integers less than or equal to n. Note that 0 factorial equals 1 and 1 factorial equals 1. Remember, we always have special rules when it comes to 0 and 1. For example, 4 factorial would be the product 4 times 3 times 2 times 1, and that equals 24. I'll show you in a little bit. Here, we're going to go through some examples. So here we have number 1. We have 10 factorial, which equals 10 times 9 times 8 times 7 times 6 times 5 times all the way down to 2. Well, let's go and write 4 times 3 times 2 times 1. Now you can write that out manually. There are ways to write it in the calculator, which I'll show you in a little bit. But first, we're just going to go ahead and find that number. So when we enter that into the calculator, we get 362,8800. So it's 3,000,000. 3,628,800. Here for part 2, we have 8 factorial over 3 factorial. Now this one's kind of interesting because what you have is when you have to write it all out, you have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now remember, the 1's not necessarily that important because when you multiply by 1, so it's really not necessary to write. Here we have 3 times 2 also times 1. But look, these cancel out. So if you're doing this more manually, you could just say 8 times 7 times 6 times 5 times 4. Oops. And it's going to equal 6,720. Okay? So that's how you do that. Now, really quick, one thing I did want to show you was this is an online free scientific calculator. So when you go on there at first, you could say this. You can do 7 and go over to function. You see this exclamation point and enter. That's so you can check your answers. You should understand the process of factorials, especially in this example, because you see here how you were able to cancel out some numbers. It actually helped you. So that's an important thing to understand. If you have any questions about that, let me know. Many real-life problems involve counting the numbers of ways that things can be chosen, and making the choices sometimes order matters and sometimes it does not. For example, suppose you are ordering a 3-topping pizza. Whether you say pepperoni, mushrooms, and onions, or mushrooms, onions, and pepperoni, you'll get the same pizza. The order doesn't matter. Suppose you're choosing numbers and letters for a license plate. The license plate KC157 is different from CK751. Even though they use the same letters and numbers, the order matters. And this is an important difference because it means that instead of just saying 1, 2, 3 and 2, 3, 1 being the same thing and only counting once, now we're going to count them separately. So suppose that you have 3 letters in an urn. You are told to choose 2 letters without replacement. That is, you'll choose a letter, not return it to the urn, and then choose another letter. How many ways, different results, are there to do this? So let's just take a look and see what we've got. So remember, we've got A, B, and C, right? So let's see if we were doing it. It says if order doesn't matter, what are the different results? So if order doesn't matter, let's say on the first one, we pull an A. Okay, so then after A, we can either get B or C. So you'd either have A, B, or A, C. Now, let's say we pull B on the second one, and then we pull an A. Well, that doesn't matter. We already have that there. And order, in this case, order doesn't matter. So we don't care if we get A, B, or BA. So we're not going to count BA again. All right, so then we could get BC. All right, now if we pull a C on the first one, if we get CA, oh, we already have CA. But if we get CB, we already have BC, and we don't care about order. So for that first one, if order doesn't matter, what are the different results? You can have AB, AC, or BC. That's 3 possible results. That's for part A. Part B says, if the order does matter, what are the different results? Well, now we're looking at order. Remember when it says without replacement, you can't duplicate. So you can't get AA. We're not replacing. So if the order does matter, so then we would say, okay, if you pull an A on the first one, you can either get AB or AC. All right, so then if you pull a B first, now if we get BA, that does matter because here it says order does matter, so we're counting both AB and BA. So we have BA, and then we could pull a B and get BC. Now if we pull a C first, we could get CA. Again, we already have AC here, but we are counting it because order does matter this time. And same then if we get C and we get CB. So now we have 6 outcomes. So if order doesn't matter, we have 3 outcomes, and if order does matter, we have 6. All right, let's go down. So here's the exact same thing, the same exact thing we're looking at without replacement, and we're looking at the different order, okay? So that's the example of how you pull them out. Now, let's look at how we can look at this in a more systematic way. You have 2 different words are used. Order does not matter, those are combinations. Order does matter, those are called permutations. There are 2 numbers that are important. N is the total number of items that you are choosing from, and R is the number of items that you are choosing. Combinations, when R items are chosen out of the N possibilities without replacement, where the order of selection is not important. Now think of a combination as a bunch of items that are thrown in a basket. All that matters is what ends up in the basket, not how they got there. So again, combinations, we do not care about the order. So there are, and it's this, that's N and R and a C in the middle, combinations of size R that may be selected from among N choices without replacement, where order doesn't matter. So this is the formula for that. So we have that combination of NR equals N factorial over N minus R factorial R factorial. So let's go back up to our example up here. So here, how many do we have for N? N was the number of outcomes, right? The number of possibilities without replacement. So in our case, this example, N equals 3. And then R represents the number of items that you are choosing. So R equals 1. So if we were to write this out for what we just did for the combination, that's where order does not matter. So that was our first example where our answer was 3. We would say this equals 3 factorial over 3 minus, 1. I was already thinking the answer in my head, sorry. 1 factorial times 1 factorial. So this equals 3 factorial over, and so this is 2. And remember, 1 factorial is just 1. So we have 2 factorial. And remember, when we wrote that out earlier, that's the same thing as saying 3 times 2 over 2, and that cancels and that equals 3. So yes, this is a little bit more laborious than counting them up manually for a small number like this, but it's that example that shows us that we get the same answer. So let's go down and look at some more examples. So here it says to find the number of combinations, identify N and R and substitute into the above formula and evaluate. Examples, in how many ways can 4 pizza toppings be chosen from 12 available toppings? So we just said pizza toppings, we don't care about the order. I don't care what order you ordered it. If you say, like I said, pepperoni and mushrooms, you're going to get pepperoni and mushrooms, although that would not be a pizza I would choose. So here, for example 1, we have N equals 12 options and R equals 4 choices that we're making. So we would say, in this one, you can say 12, 4 equals, and we have N factorial, 12 factorial, over N minus R, which is 12 minus 4 factorial, times R factorial, which is 4 factorial. This gives us 12 factorial over 8 factorial times 4 factorial. All right, now you can do this manually. Again, we've already kind of gone through how to do that. I will say that you can do this in your calculator. And when I'll show you down below, down here, there's a way to do combinations and permutations in your calculator. See how you can do it here. And if you have a graphing calculator, you can do it like that. If you have a scientific calculator, you can do it like this. So I'll show you on, let me see, back over here on our original scientific calculator I was showing you. This is just a free one. If you guys don't have one, you are more than welcome to use this, called Desmos or Desmos. But when you put it in, you're going to put N comma R, and you can see it again. I want to show you where in the lesson is so you can reference this later. See, here's for permutations or combinations, and it tells you can do the value. See how you put the numbers in there like that? This one looks a little bit different. We're going to put, I believe you do N comma R, 12. Okay, so yeah, so in this one you get 495. But just to point out again, so when you do it in this online free one, you would select N, that the combination, and then you would do N. This is N comma R. Here you're going to see it for permutation, but this is if you're doing it on the calculator you have with you, like the that Texas Instrument 30X, then you can do it this way, where it shows you putting it in. See how you can see right here 12 and then 4 after. Okay. So just to use that as a handy little reference tool if you're having a hard time with it. So anyway, back to the example, we can select 495 different combinations from 12 pizza toppings with 4 choices. So let's do example number 2. At a baby shower, 17 guests are in attendance and 5 of them are randomly selected to receive a door prize. If all 5 prizes are identical, in how many ways can the prizes be awarded? So the idea is that we're not worried about which different prizes. We're just worried about how many different ways they can be awarded to the 5 people. So in this case, our N is equal to 17 and R is equal to 5. So again, this would equal, going back up to our formula right here, we would have 17C5 combination equals 17 factorial over 17 minus 5 factorial times 5 factorial. So if you, like I said, you can either do out the factorials, or you can do, you can also do the thing that we were showing on the calculator. Actually, let me go ahead and show you how to do it in the calculator again. So here we would choose the combination again and do 17 comma 5. Oops. There we go. It'd be 6,188. But I do want to make sure you guys all understand this factorial. It is important. Okay. Let's see. All right, that's it for part 1, and I'm going to pick up in part 2. Let me know if you have any questions about combinations so far.